So, till now we have finished settlements. So, I have covered settlement calculations for sand as well as clay, immediate as well as consolidation settlement, and last class I have covered also by means of stress path method how to calculate consolidation settlement. Now, we can start a new, that is your stress distribution in soil. Stress distribution in soil. So, basically if I put it stress distribution in soil, I can put it in two parts. One is your in situ stress, second is your stress due to foundation loading, stress due to foundation loading. So, primarily this is important for all of us design of foundations, because depending upon your size of the foundations, how much is your increase in stress in a soil mass. And now, if you come back to in situ stress, in situ stresses due to means stress due to overburden are called in situ or geostatic stress. Stress due to overburden are called in situ or geostatic stresses. So, take an example here, the layer of soil, and here is your water table, then there is a soil element here, and this is your sigma V, and this is your sigma H, and then at a depth Z below water table, this is your H, then from the ground surface it is at a depth Z. So, here if you look at here, this will be your sigma V, and this part of here will be U 0, and this will be your sigma V prime. So, vertical stress sigma V is equal to gamma Z, and then total horizontal stress sigma H is equal to K sigma V, which is equal to K gamma Z. So, sigma V prime, which is equal to sigma V minus U 0, which is equal to gamma Z minus gamma W into H, and sigma H prime is equal to sigma H minus U 0, which is equal to K gamma Z minus gamma W into H, which is equal to K 0 sigma V prime. K 0 is your coefficient of earth pressure, K 0 is equal to coefficient of earth pressure at rest. So, this is about your stress, that means in situ stresses. Now come to stress due to your foundation loading. Stress due to your foundation loading. Now, there are many cases stress due to your foundation loading. If I say what type of loading comes into the foundations, it may be a point load, it may be a circular loaded. Generally foundations are constructed on isolated footings, strip footings, combined footings, raft foundations as well as rectangular foundations. So, it may be a rectangular loaded, sometimes it may be a line load or foundation of any shape, any shape. So, what will happen stress due to foundation loading? Start with a stress caused by a point load. This is called Boussinesq theory. Boussinesq 1985 obtained a solution for stress and determined the interior of soil mass due to vertical point load applied at the ground surface. Take an example. This has been given by Boussinesq, Boussinesq 1985. So, if I draw it a 3-dimensional figure here, this is your z direction, this is your x directions and this part is your y directions. Now, consider an element, soil element, here it is like this, then (3D) element. Here you can show it, if you take a point here, then you can show it this way, this way, this way, and here you are showing this way, and this will be your delta sigma z. Similarly, here it is coming delta sigma x. So, it will have this way. Then if I consider this will be my distance of from this point to this point, this will be x and this part will be your y and this is your x, this is your x, and this distance from here to here is your r, and from here to particularly here ground surface to at the middle, this will be your z. The detailed derivation is out of scope because this is a undergraduate course. So, what are the assumptions Boussinesq has taken? Soil is homogeneous, isotropic, then elastic. Now, they derived it, increase in stress, that means lateral stress as well as vertical stress as well as y. So, delta sigma x, which is equal to p by 2 pi 3 x square z by L fib minus 1 minus 2 mu into x square minus y square divided by L r square into L plus z plus y square z by L q r square. So, similarly they have also derived for delta y 3 dimensional, delta sigma z vertical stress, increase in vertical stress, which is your 3 p zq by 2 pi L to the power 5, which is equal to 3 p by 2 pi zq by r square plus z square to the power 5 by 2, where r is equal to x square plus y square root over and L is equal to, this is your L, distance from here to here, L is equal to x square plus y square plus z square root over, which is equal to r square plus z square root over. Mu is equal to is your Poisson's ratio. So, Boussinesq has given, suppose there is a point load here, I forgot here, suppose there is a point load P at the ground surface. Because of this point load, what will happen? Stress below the point load as well as nearby at a distance x or at a distance r or at a distance L below the ground surface, what is your stress variations because of your point loading. So, then come to its physical part, I will discuss one by one. So, vertical stress I can write it, vertical stress delta sigma z is independent of Poisson's ratio. So, if I can write it, delta sigma z is equal to p by z square into 3 by 2 pi 1 by r by z whole square plus 1 to the by 5 by 2, which is equal to p by z square into I. I is nothing but is your influence factor or influence coefficient. I is nothing but is your influence factor or coefficient. Influence factor or coefficient. So, there are charts given, variation of I for various value of gamma z, in any textbook you can find it out, variation of I, different value of I, variation of I for various value of r by z. R is your distance and z is your vertical distance. So, when r is equal to 0, that means when r is equal to 0, at that point I influence factor is equal to 0.4775. Vertical stress directly below the foundation load, just directly below the point load, then it is your r is equal to 0 means, if you come back here, r is equal to 0, this r is equal to 0, that means vertical stress below the point load just at this point. So, then it will be I is equal to 0.4775, then in that case sigma z is equal to 0.4775 q by z square, or q, instead of writing q you can write it q, or maybe it is a p. P by Z square. Now comes to next part, Z tends to 0, that means depth changes to 0, what will happen? Z is equal to 0, Z is equal to 0 means this depth is equal to 0, R is equal to 0, fine. Next step is your Z is equal to 0. Once Z is equal to 0, what will happen? It will be infinity. Sigma Z tends to infinity, which is not true. There will be some value at Z is equal to 0. It is not going to tends to 0, theoretically as it says, it is not tends to 0. So, this is part of this your point load, then giving this value of your distance r, you can find it out what is your delta sigma z or sigma z because of your point load. Then r is equal to 0, the I is equal to 0.4775, sigma z is equal to 0.4775, q or p, this is not q by p, this will be, let me write it because here I have written p, noting q or p by z square. Now come to next part, vertical stress distribution diagrams. First one is your vertical stress isobar diagrams. Second one is your vertical stress distribution on a horizontal plane below a ground surface. Vertical stress distribution on a horizontal plane below the ground surface. Third one is your vertical stress distribution with depth at a distance r away from the line of action. Vertical stress distribution with depth at a distance r away from the line of action, away from the line of action. So, if I draw it here, what you are supposed to get it? This is your point load P, I am getting a vertical stress, that means isobar diagrams. This is my isobar. This is case 1. Second one is your vertical stress distribution on a horizontal plane. This is my horizontal plane at a distance of z. How it varies? And third one is your vertical stress distribution below the ground surface at a distance r from the point load below the ground surface, how it varies. So, these are the three cases. One is your vertical stress or isobar diagrams, second is your vertical stress distribution on a horizontal plane below the ground surface, third one is your vertical stress distribution with depth at a distance r away from the line of the action. Now, what is isobar? Very simple question. What is isobar? If this is my ground surface, there is a point load here, suppose say P or maybe Q, then this is your central line along the line of your point load, and this will be my isobar. What is the definition of the isobar? If I write it isobar, it is a line joining all points of equal vertical stress below the ground surface. I am just writing it out, line joining all points of equal vertical stress below the ground surface. So, line joining all points of equal vertical stress below the ground surface. What does it mean, isobar? So, it is called isobar, also it is called pressure bulb. That means the point here, 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 here. These are all equal vertical stresses below the ground surface. Now, for a loading system, for a particular loading system, you have, for a loading system, you have many, for a loading system many isobar can be drawn. So, isobar is called a pressure bulb. It is like a kind of onion shape pressure bulb. Now, if I go to the second part of this, first part is your isobar definition has been made. If I go to the same point, if I am discussing here isobar diagrams, equal points, let us say delta sigma z is equal to I into Q by z square. Here it is a Q, let us put it as a not P, let us put it as a Q, it is your Q by z square. So, assume sigma z is equal to 0.1 Q. So, that means 0.1 cube is equal to I into B by z square, whereas I is equal to 0.1 z square. Now, consider this. This is your depth, this is your IB or I, this is your R by Z, this is your R. So, depth put it 0.25, I am just calculating very few, you can calculate and you can see the books. Then this is your 0.5 and this is your 0.75 and this is your 1.0. So, it is coming out to be 0.006 and this is your 2.17, this is 0.543 and 0.5 is your 0.025 and this is your 1.5 and this part is your 0.75 and this will be your 0.056 and this will be 1.16 and this will be 0.87. Now, this will be 0.1, 0.93 and this will be 0.93. If I go up to 2 point, like this, if I continue, let us say if I go up to 2.185, so here will be 0.4775 and here will be 0.006 0, 0, 0, 0.000. Now draw it. For particular case you draw it, I am drawing it. Look at here, this is my point load which is your 0.1 q, and this is what I am getting a pressure bulb, sorry, this is a q and this is your 0.1 q pressure intensity, and at this point R is equal to 0, at this point also R is equal to 0. So, this will be your Z, this part will be your Z. So, this distance will be somewhere else 2.25. Now, we can find it out. Infinity values, as I said, you can assume it sigma Z is equal to 0.1 q. So, R is equal to 0, R by Z is equal to 0, here at the surface it should be 0.4775, it is not supposed to be 0, it will start from here, so that this part will be 0.4775, then all other values will be 0. So, similarly you can plot for different pressure intensity. Here it is 0.1 q, you can plot it 0.2 q, 0.3 q, 0.5 q, all you can plot it. This is what is about your isobar. So, I will start next class vertical stress distribution on a horizontal plane. I will stop it here because this is a long, this will be continuing in a long. Thank you.